Lesson 3.3 is graphs and identities for trigonometric functions. Let me just start by saying that this part, identities, this is a huge topic. And if you had a course in trigonometry, you know you can have pages and pages and pages of trigonometric identities. What we discuss will be what I consider the bare minimal to get you ready for a calculus course. So the last two lessons really is where we discuss the trigonometric functions, sine, cosine, and then the other four, tangent, secant, cotangent, and cosecant. So let's get started talking about the graphs of sine and cosine. Before I do, let's draw a unit circle because we can really think about angles. Now you'll notice in this chart, this is not all the possible values we know. What I am going to fill out is just some of the sine and cosine values at multiples of pi over 2. And then I'll use this to graph the functions of sine and the function cosine. So we start over here at 0. I will start right here. At 0, this would be here. Well, you notice the cosine is 1 and the sine is 0. Now at pi over 2, this is here. The sine is 1. Cosine is 0. At pi, we are out here. Cosine is minus 1. Sine is 0. 3 pi over 2. Sine is negative 1. And cosine is 0. And then you notice at 2 pi, we have the same terminal side as angle 0. Cosine is 1. Sine is 0. Now I just have these two negative angles that I want to write down. Negative pi over 2, we would move this direction, is here. You see cosine is 0, sine is negative 1. And finally, negative pi would be here. Same terminal side as the angle pi. We get that the cosine is negative 1, sine is 0. So we can use these values of sine, these values of cosine to help us graph the functions. Let me remove my unit circle. If we look along the first row, these are the y values for cosine. We have minus 1, 0, 1, 0, minus 1, 0, and 1. Well, the question is, how do we draw it from here? It is definitely not straight lines because that's not how the cosine goes. If you remember, we are reading off around a unit circle. The graph of the cosine looks something like this. This will continue though. This pattern continues like this in both directions. The way that I remember this is I'm trying to remember the graph of the sine of the cosine is starting at 0, which here's x equals 0. Cosine goes high, 0, low, 0, high, like this. And then it just repeats this pattern. Now let's look at the sine. If we look at the bottom row here, we have 0, minus 1, 0, 1, 0, minus 1, 0. So this will look something like this. And this continues, this pattern. The way I remember sine, once again, starting at 0, it goes 0, high, 0, low, 0. But this pattern, it will continue really in both directions, repeating. These are the basic shapes of these graphs. Now let's make some observations here. The domain is all real numbers, minus infinity to infinity. We can evaluate the sine and cosine at any real number, but the range is not. The range is this closed interval, minus 1 to 1. We see it in both of the graphs. And the other thing to mention, I said this verbally, that this pattern is repeating, but what that says is that these are periodic functions. So this, let me back up a page, this shape, it repeats again. So we see here, and then we see again and again and again. And that means periodic. And the period here is 2 pi for both of these, meaning every 2 pi, the exact same pattern repeats. And for cosine, the pattern is high, 0, low, 0, high. If you start at 0, and for sine, it's 0, high, 0, low, 0, if you start at 0. So sine and cosine are periodic functions with period 2 pi. This was the important comment and observation to make. If we move on to the other trigonometric functions, tangent, cotangent, secant, and cosecant, it is very important to understand these functions do not have domain minus infinity to infinity. These functions fundamentally are something divided by something. We know we cannot divide by 0 in math. So how can we pair them here? Let me draw a vertical line. Tangent is sine over cosine. And the other one that has a something over cosine is the secant, which is 1 over cosine. And then we have cotangent, which is cosine over sine. And we also have cosecant, which is 1 over sine. So you notice the tangent and secant both have cosine in the denominator. So these two are undefined when the cosine is 0. And then cotangent and cosecant, these two are undefined when the sine is 0, because both of these have sine in the denominator. So that's just an important observation I want to make. But let's look at the graphs of these other 4 trig functions. This seems like a lot to look at. Let me draw my vertical line once again to separate. You see over here, the tangent and the secant, you see these are all undefined at the exact same place. It's namely when the cosine is 0. And then here with the cosecant and cotangent, these two are also undefined at the exact same place. It's when the sine is 0. What's important to get out of this is, number one, these 4 trigonometric functions are not defined on the whole real line. It's important to understand when secant and tangent are undefined, when cosecant and cotangent are undefined. And then it's also very important to understand the basic shape of, back it up to, sine and cosine. These are fundamental to calculus and trigonometry and many other courses. At this point, I want to move into the identities part of this lesson. So far, we've talked about some fundamental identities. We have talked about sort of the defining identities for tangent, cotangent, secant, cosecant, and then we talked about this. Sine squared plus cosine squared is 1. All of this we discussed in the last 2 lessons. But really, we can get 2 more identities from this one, which I would say are maybe not as important as sine squared plus cosine squared is 1, but almost. So they're very important. We use them. Okay, but they involve the other 4 trig functions. So for the first one I can talk about, let's take this identity and just divide by cosine squared. We get sine squared over cosine squared, plus we have cosine squared over cosine squared, and then we have that equals 1 over cosine squared. I just took this known identity, which was from 2 lessons ago, and divide every single entry by the same thing, namely cosine squared. Well, you see what we get out of this? We get a new identity, which is fantastic. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And then 1 over cosine squared is secant squared. So this is another identity. And personally, I don't memorize this as a new identity. Anytime I need an identity that involves tangents and secants, and I remember it's kind of like the sine squared plus cosine squared equals 1 identity, I just rederive it every time, and I can get this. Now the other one, we just take sine squared plus cosine squared is 1, and we divide by sine squared. So here you notice we get sine squared theta over sine squared theta. Then we have cosine squared theta over sine squared theta. And then this will be 1 over sine squared theta. It's very similar to the last one we just did. But you see, once again, this is another identity. From this, we see 1 plus the cotangent squared equals cosecant squared. But for me personally, just like above, I don't memorize this. Anytime I want to use an identity that involves cotangents and cosecants, and it's kind of like sine squared plus cosine squared equals 1, I just divide every term by sine squared and I rederive it. That way I don't have to try to memorize, is the 1 over here Well, no. Or like this one is a 1 over here. Okay. Well, no for that too. I don't memorize it because I can just take sine squared plus cosine squared is 1 and divide by either sine squared or cosine squared to get these two other identities. So we will do a few examples of using all of these trig identities here to simplify things. As I said at the beginning, there are many, many, many more trig identities, but I'm focusing on these few for this lesson. So here, this first one, how are we going to simplify this? Well, in my mind, the easiest thing to do is break everything into sines and cosines. So in my numerator, cotangent is cosine over sine. Tangent is sine over cosine. And then secant, which is in my denominator, is 1 over cosine. Now, what can I do? Well, I can invert and multiply. When I do, you notice I will be multiplying this entire thing by cosine theta over 1. And so this first term turns into cosine squared theta over sine theta. And then the second term becomes sine theta. Now ask yourself, can you simplify this more? We can. In fact, I can get a common denominator and add these two terms. The common denominator is just sine theta. So what I can do is multiply this by sine theta, divided by sine theta, and you see what happens. I get cosine squared plus sine squared over sine. Now, sine squared plus cosine squared is 1. And so we get 1 over the sine of theta. Another way you could write that is the cosecant. So this, which was cotangent plus tangent over secant, this simplified a lot to just the cosecant of theta. This will be my final answer here. Next one. Once again, this looks quite complicated, but let's just start breaking this into sines and cosines and see how much we can simplify. This first one, we have 3 sines cubed t times 1 over sine t. And then we have cosine squared. I'll leave that alone for the moment. But then you notice I have 2 sine t, cosine t, and then cotangent is cosine over sine. Now we're going to be in really great shape. You notice the first term is 3 sine squared t, because here we have a sine cubed over sine. That will become sine squared. And then the second term I'll leave alone for the moment. This is cosine squared. Now, all of this, sine divided by sine, here and here, this becomes 1. So I'm left with 2 cosine squared. And now you see I have 3 times, well, I have a sine squared and I have cosine squared, because right here, here's 1 cosine squared and here's 2. Altogether, this is 3 cosine squared. Now, once again, sine squared plus cosine squared is 1. This is just 3. So this once again simplified significantly. It looked quite complicated at the start. And using the trigonometric identities we have discussed, we simplify this to 3. Now here's one more on this page. This one's much shorter. We just have tangent times cotangent. But what happens when you break this into sines and cosines? Tangent is sine over cosine. And cotangent is cosine over sine. So now look at this. This is just 1. All 3 of those looked kind of complicated to start, but after we simplified, we got quite simple looking answers. Now let's do one more in this lesson, and that's the following. We want to use trigonometric identities to prove or disprove this, which I'm claiming is an identity. Maybe it's an identity, maybe it's not. We either want to prove that it holds or show that it doesn't. So let's work with the left-hand side first. I see a sum of 2 fractions. And so what I want to do here is get a common denominator. Common denominator in this case will just be the product of the two denominators. So this, let's see, I will take the first one, 1 plus cosine x, and multiply this by 1 minus cosine x divided by 1 minus cosine x, like this. Then, to get a common denominator on the second term, I will multiply this fraction by 1 plus cosine x divided by 1 plus cosine x. So let's see what we have. For the moment, I'll leave my denominator as a product. We have 1 minus cosine x times 1 plus cosine x. Now you see I have 1 minus cosine x plus 1 plus cosine x. Well, we can keep going here with the left-hand side. You notice my numerator, the plus and minus cosine x add to 0. So my numerator is just 2. And then my denominator, if you multiply all of this out, first, outer, inner, last, the inner and the outer add to 0. I have a positive cosine x and a negative cosine x. So what I get here is 1 minus cosine squared x. Now I can take one more step, because maybe I'll write it small here at the top. Recall we have sine squared plus cosine squared is 1. This is our most important trigonometric identity. So if I subtract cosine squared from both sides, I have sine squared x is 1 minus cosine squared x. So this is the one that I'm going to use here. You see in my denominator, I have 1 minus cosine squared x. So this is just, we have sine squared x in the denominator. So this simplified, in fact, I can write it in terms of a cosecant. This is 2 cosecant squared x. So this is as simple as I can make the left-hand side. Now, notice that 2 cosecant squared x is definitely not equal to 2 cotangent x cosecant x. If it was, that would say that the cotangent has to equal the cosecant, and that is not generally true. So this identity, this identity does not hold. Okay, it is not a trigonometric identity. So what we did in this was we disproved. Now we can take this further. Let's look at a graph of both of these, because the left-hand side is this and the right-hand side is this. Okay, let's open up Desmos for a moment. What we're looking at here, first of all, in blue and in green, is the right-hand side and left-hand side of our original equation. We were trying to figure out if it held. And instead of just graphing, I really wanted to use trigonometric identities that we know and are focusing on in this lesson. But now that we've done that, you can look at the graph and see that these two are not equal. 1 over 1 plus cosine x plus 1 over 1 minus cosine x is definitely not equal to 2 cosecant x cotangent x. Okay, we can see looking at the graph. But what we did was you see, this is what we did show held, that the green and the red, in fact, you can see this graphically, that they are the same. The green and the red are the same functions, right? And then, well, of course, the blue and the red are not the same either. But I like looking at this graphically after working with it, just using trigonometric identities. We can see these two definitely not equal. This is the end of lesson 3.3. You can move on to the exercises now. Thank you so much.